Welcome to The Explainer. Today, we're going to break down a concept that's, well, fundamental in computer science, but it powers way more of your digital life than you probably realize. I'm talking about the linked list.
All right, so here's the plan. First, what even is a linked list? Then we'll see how these things called pointers make it all work. We'll even solve a cool puzzle with them. And finally, we'll see where they pop up in the apps you're using right now.
All right, Section 1. What is a linked list? Let's talk about moving beyond those rigid rows you might be used to.
Okay, so to really wrap your head around a linked list, it helps to compare it to something we all know, an array. An array, it's like a train on a fixed track. All the cars are right next to each other in a neat, contiguous block of memory. Super rigid. A linked list? Totally different vibe. It's more like a scavenger hunt. Each clue doesn't just give you a piece of the prize, it tells you where to find the next clue. And that next clue could be anywhere.
So, what's the secret sauce for this scavenger hunt? It all comes down to this thing called a node. It's the fundamental building block, and honestly, it's super simple. Each node is just a little container with two parts. First, you've got the data itself, the actual information it's holding. And second, you have the pointer. Think of it as the next clue. It's basically an address that points the way to the next node in the chain.
So this whole structure has some pretty huge upsides. Look at the pros. You can grow or shrink it on the fly, super dynamic. And adding or removing an item is crazy efficient because you're just rewiring a couple of those pointers. But like everything in life, there's a catch. The cons are real. You lose what's called random access. You can't just say, hey, give me the 50th item. Nope, you got to start at the head and follow the chain one by one. And yeah, all those pointers take up a little extra memory. So it's a trade-off, right? Flexibility for the price of direct access.
Okay, next up, pointers in action. Let's look at the different flavors of this chain.
So you've basically got three main flavors. First is the singly linked list. Super simple. Each node points to the next one. It's a one-way street. You can only go forward. Then, things get a little more interesting with a doubly linked list. Here, each node has two pointers, one to the next node and another to the previous one. This is a game changer because now you can go forwards and backwards. And finally, you've got the circular linked list. This one's kind of cool. The last node, instead of pointing to nothing, points all the way back to the beginning, creating, well, a circle.
Okay, this is where it gets really cool. Let's talk about solving puzzles with pointers. We're going to look at a famous one, the tortoise and the hare.
So, let's set up a classic puzzle. Imagine you're given a linked list. It could be a straight path that just ends, or it could have a loop in it somewhere, where the chain doubles back on itself. How in the world can you figure out if there's a loop without getting stuck in it forever?
The answer is it's so clever. It's an algorithm called Floyd's cycle finding algorithm, but everyone calls it the tortoise and the hare for a reason. Here's what you do. You create two pointers, and they both start at the very beginning of the list. You've got your slow pointer, the tortoise, who just plods along, moving one node at a time. And then you have your fast pointer, the hare, who's zipping ahead, moving two nodes at a time.
And here's the magic. If the list is just a straight line, the fast pointer will eventually just run off the end. No big deal. But if there's a loop, think about it. The fast pointer will get into that loop first and start running in circles. The slow pointer will eventually get into the loop too. And since the fast one is moving twice as fast, it's absolutely guaranteed to eventually lap the slow one. The second they meet on the same node, boom. You found your loop. It's so simple, but so brilliant. Just a fantastic aha moment.
Okay, so all this might sound a little theoretical, right? But I promise you, you are using linked lists constantly. Let's take this from theory and bring it right into your browser tab.
Let me ask you something. You ever hit the back button in your web browser or the forward button? Of course you have. But have you ever stopped to think about how that actually works? How does it know exactly where you were before? Well, you're looking at a perfect real-world example of a doubly linked list. Every single web page you visit is a node in that list. When you click a link, a new node gets created, and its previous pointer links back to the page you just left. So when you click back, all your browser's doing is following that prev pointer. Click forward, you guessed it, it's just following the next pointer. It's that elegant.
Okay, here's another huge one. It's called an LRU cache, which stands for least recently used. Now imagine you have a limited amount of really fast memory. You want to keep the most important stuff in there, right? But how do you decide what to kick out when it gets full? Well, an LRU cache has a simple, smart rule. Get rid of the stuff you haven't used in the longest time.
So how do you build one of these efficiently? You use a brilliant 1-2 punch of data structures. You start with a doubly linked list. Its job is to keep track of what's been used recently. Every time you access a piece of data, you move its node to the very front of the list. This means the thing at the very end of the list is, by definition, the least recently used. Perfect. But wait, finding something in a long list is slow. And that's where the second part comes in, a hash map. The hash map is like an index in a book. It lets you find any node in the list instantly in what we call O of 1, or constant time. So you get the best of both worlds. The linked list maintains the order, and the hash map gives you lightning fast access.
And trust me, this is not just some academic exercise. This is running everywhere. Your database systems use it to make queries faster. Your computer's operating system uses it to manage memory. Even the text prediction on your phone, the thing that suggests the next word you're going to type, yep, that's often powered by an LRU cache, keeping the most likely words close at hand.
So think about that. We started with this super simple idea, a piece of data and a pointer to the next one. And from that simple chain, we get these elegant solutions for complex puzzles, and it becomes the backbone for technology we use every single second, from our web browser to massive databases. The linked list is just a perfect example of how a simple, powerful idea can change everything. It really makes you wonder, what will you build with it?